Good morning, everybody. Welcome to the fifth oral session, this UAI 2024. It's on learning algorithms. We're going to have five presentations in this session, one oral, one virtual, and the fourth are going to be here presenting for you. So, yeah, the first talk we're going to have is on cost-sensitive, uncertainty-based failure recognition for object detection. Here we have with us Moussa, and we're looking forward to your presentation.
Thank you. It's working? All right. So hi, everyone. A warm welcome from my side as well. Thank you for being here and not at the beach right now. I appreciate that. I hope the presentation will be interesting enough to compensate for that. So my name is Moussa Kassem Sbeyti. Today, I'm going to be presenting a joint work with my colleagues and supervisors, Karg, Wirth, Nadja, Klein, and Albayrak. And the topic of my presentation is, as Jalal said, cost-sensitive, uncertainty-based failure recognition for object detection. And what I want to start with is maybe, yeah, that's a motivational slide, but let's skip that and get directly to the actual motivation. Why do we need failure recognition and why it should be uncertainty-based? So current object detectors typically produce a bounding box around the object, a corresponding class, and a confidence score. But that confidence score that comes from the classification output is usually not reliable, as object detectors tend to either exhibit over or under confidence. This is also more problematic when we're dealing with noisy objects, as is the case with real-world data, where the confidence score that is based on the classification output is not reflecting at all on the localization accuracy. And here, the model would predict a bounding box that you would assume is accurate due to the high score, although that would not be the case. Another issue would be when dealing with unknown objects, where the model might mistake an object with similar characteristics to the classes that it was trained on and predict a bounding box where it shouldn't. And what you can take away from that is that we have different uncertainties at play. So we have localization uncertainty that plays a role in detecting failures of the localization head of the detector. We have the classification uncertainty that is playing a role in the classification mistakes of the detector. And when we're dealing with noisy data, it would be aleatoric uncertainty. When we're dealing with data that the model didn't necessarily see during training, we would be dealing more with epistemic uncertainty. And so we would like to investigate the multiple uncertainties and offer the detector a reject option, which the detector would, in that case, say, I would rather refrain from making a detection than giving you a false one. And so why do we think that it would work based on uncertainty? Mainly in a previous work of ours, we have shown that on average, the uncertainty, in this case, the aleatoric localization uncertainty, reflects on the state of a detection. So on average, the uncertainty of a false detection is higher than that of a correct detection. That even translates to classification, where the uncertainty on average of false positives is higher than that of true positives. However, we can see that there is an area where we still have an overlap. And an overlap means that there is a cost. So no matter where we put our threshold based on the uncertainty, we will lose correct detection while trying to remove false detections. And for that, we go for a cost-sensitive approach, has the consistency in the title, where we start with the cost matrix for the detector. So maybe I assume a lot of you do not have any experience with object detectors, so I will define what a correct detection is. A correct detection is a detection where the class is correct based on the manually labeled class, and the intersection between the box that is predicted and the box that is labeled is above a certain threshold. Usually in object detection, you use threshold between 0.5 and 0.75, so 50 to 75% overlap. Here we can see how that changes the count of false detections and correct detections. And so here are the labeled CDs and FDs. So based if the class is correct and the IOU, which is the intersection that I spoke about, is above the certain threshold. And this is what we get based on thresholding of the uncertainty. So if we have a correct detection and the thresholding actually keeps it in our detection pool, then we have no cost. if there's a false detection and the thresholding actually removes it, it also incurs no cost. So the cost of the mistakes of the model come down to the missing detections, so the correct detections that are falsely removed, and the false detections which remain in the detection pool. Now, in general, it's pretty difficult to say that, I don't know, a missing detection costs you double as much as a false detection, or half, where it's not very intuitive to define it. So how we tackle it is with a budget. Instead of defining the cost, we define the missing detection rate or the false detection rate. So for example, if we're dealing with autonomous driving, and you would say that regulations say that my detector needs to have a missing detection rate below 1%, you could say that based on my budget, I need to keep post-thresholding 99% of my CDs because I would increase my MDs only by 1%. Or you could be detecting poisonous mushrooms and say that the human body can tolerate 5% of poisonous mushrooms. So you're fine with making 5% mistakes at these, but you need to remove the other 95%. So you would put a budget on either CDs for the one use case or FTs for the other use case. So in this sense, we make it application agnostic, where depending on the application, you can intuitively define what rate are you looking for post-thresholding. That's the first step. The second step is still using the multiple uncertainties. And here you can see that if we have some value here, even if we normalize it or for the classification, it's already bound between 0 and 1, you could intuitively say everything that is below 0.7 or 70% confidence, I want to remove it. But here you can see that there are mistakes already at 8%. So the question would be, if you set your threshold now at 8%, would that even translate to the other images in the data set? And that we don't know because we can only compare the objects relatively to each other in one image. And when we combine the uncertainty, the second challenge after the first challenge, which was the overlap of the uncertainties, is how do we set automatically, we don't want to go looking at all the values, a threshold that will translate to the domain we're dealing with. And that brings us to the ROC curve. So in the ROC curve, we have two, or actually three things. The first thing is we can define where our budget should be. So if we say that we want to remove 99% of our false detection by the detector, we would set our TPR at 0.99. The blue curve that you see here is mainly using the uncertainty, and every single threshold constitutes a point on the curve. How many false detections would we get, and how many correct detections would we lose, which would be the FPR and that. And so if you want to keep a lot of CDs and not increase your MDs, you would bound your FPR. If you want to detect as many FDs as possible based on some budget, you bound your TPR. And what you get out of that is automatically the threshold, but also the error rate corresponding to what the threshold will make you lose, so to say. And so we have two defined metrics that we define here. One is for the UK use case where you bound your FDs with a budget. And so it tells you how many CDs would you keep for that bound FDs rate. Or the second use case would be when you say that I'm only ready to lose X amount of CDs, how many FDs would I get for that? But that only reflects on the thresholding performance. So the next step would be, how do we translate that to the detector performance? And so we check a couple of metrics and we find the requirements, or in this case, the inequalities that will tell you at which point does it start making sense to actually use the threshold. Because if you're losing more detections than you're actually gaining by removing the false detections, then it's not really helpful. And so we automate the thresholding and its evaluation, and then we move to the optimal combination. So we said we have multiple uncertainties. Some of them are bound between 0 and 1 because there are probabilities. Others are between 0 and infinity, such as for the regression, for the localization. And so we don't want to normalize and add them together. Some may, in one data set, the localization uncertainty might play a bigger role. The classification might play a bigger role than the other. So we want to optimize the process. So what we do is, we have the dot product, or the weighted sum of the uncertainties. We have a weight matrix, or weight vector in this case, that we multiply our uncertainties with, and that we optimize. So we have a loop that starts with using the summed uncertainty. So in the end, we would have only one value per detection. We generate this curve. Then we calculate the loss, which is the error rates that we see here in black. over the IU thresholds that usually are used. So we get an average there, and then we repeat. So we have any black box optimization, hyperparameter, Bayesian optimization, anything that you can use to optimize the parameters, which are in this case only the weights. So we run this, it converges usually to the weights that would give you the best blue curve that goes into the corner of 0, 1, so the upper left corner. There you would have the least mistakes for the most recognition. So with that, how does that all come together? We have any detector with the output, which is the classification and the localization, as well as the corresponding uncertainty for that. We take these detections and the uncertainty, and we feed them to our optimization loop after first, of course, as I said, selecting a budget on either the FDs or CDs. Then what we would get out of it from this black box optimization is the weight vector. From the ROC curve, the optimal threshold for the budget that we give. Also, our evaluation metrics would give you a proper insight on how well it's performing. And then you can take the sum of the uncertainty, the weighted sum of the uncertainties, compare it to your threshold, and filter your detections. So based on the budget you set, either here or there, you would have CDs that will go missing as you falsely remove them via thresholding, and FTs that correctly become background as they belong. And there you have full control on either the amount of CDs that you lose or FDs that you correctly remove. So what uncertainties do we use? In the first couple of slides, I mentioned epistemic and aleatoric. So epistemic, as generally known, the model uncertainty, where you see that, for example, there's missing data, the model is unsure about the techniques that area, or data uncertainty, which is the aleatoric one, where you would have noisy data. For the epistemic, we use off-the-shelf MC dropout. Due to its complexity, computational complexity, we also use entropy for the classification uncertainty over the logits or the classification output. For the aleatoric, we use loss attenuation, which consists of extending the output from the 4 parameters for the bounding box to 8, mainly the 4 means and the standard deviations or variance to set a distribution on each coordinate. And then you would fit that via the model itself with a term that you add to your localization loss. What data set to use? One data set is BDD 100K. It's a relatively large data set, a lot of difficult scenarios, also very noisy. You can see already here, as a human, you can barely see the cars. Another data set is TT, relatively small, high fidelity. You see it's also very clear, the resolution is very high. And also as an additional independent evaluation set, we take CODA, which is the real-world corner case and auto-distribution objects data set that we test our model that is pre-trained on BDD. How does it perform when we shift the domain to CODA, which is taken on completely different continents? Our detector is efficient bet, D0. And the first thing we see already is that MC dropout would be very expensive, as expected, depending also on how many iterations you would do during inference. Loss attenuation is slightly faster, but that's only because we extended the parameters from 4 to 8, and 8 is necessary for Tensor cores and NVIDIA GPUs to be used, whereas 4 would use CUDA cores. And then we continue to investigate performance. So what we want to get here is, are we actually deteriorating the detector by implementing our uncertainty estimation methods? And what we see that, at least for loss attenuation, first, there is no inference time cost. Second, the performance is more or less similar to the baseline. For example, for BDD and CODA, MC dropout is particularly helpful as the dataset actually requires the added variability in the model. And so regardless of which uncertainty estimation methods, in regard to performance, we are still better than the baseline that has no uncertainty estimation methods. So now we covered that, all right, if we, for example, only use loss attenuation, we have no incurred costs in the detector. The next step would be to investigate the multiple uncertainties, whether it's the epistemic, aleatoric classification, localization, the entropy, the normalized version of the localization uncertainty based on the bounding box area, the calibrated version on a validation set that we have for each data set, and the uncertainty from a model that usually here are with MC dropout and loss attenuation, or a model that has no MC dropout. So here what we're trying to see is, can we get rid of the epistemic uncertainty, or is the epistemic uncertainty really necessary? And so first thing we see is this overlap that I spoke about originally. is present for all of the uncertainties. So regardless which uncertainty you use, regardless of how much calibration you do, you will not end up with a perfect separation between false detections and correct detections. Then we check over the different IU thresholds that I mentioned that are the most used in object detection, which uncertainty performs best in a matter of recognition. If we take the budget of an example, we give up 5% of our correct detections. We see that mostly here the blue curve is the calibrated aleatoric localization uncertainty from a model only with loss attenuation, or in this case for Kitty, it's a calibrated entropy. And that's also, again, reflects on the characteristic of the data set. So for example, for BDD, there's a lot of traffic lights, traffic sign, tiny, very far, the model is struggling with the localization. Whereas for Kitty, there are no classes for traffic and signs and lights. And so mostly what the model is struggling with is the classification, because person sitting is a class, whereas pedestrian is as well, and therefore it's confusing both. Then we check mainly the budget. So how does the budget, if we vary the budget, affect the relationship between the uncertainties to each other? And we see that regardless of the budget, the performance of the one uncertainty of the other remains very similar. And then for our optimization, we check, we keep the epistemic localization uncertainty to actually verify our hypothesis that we can, that it's redundant and that the entropy and the aleatoric localization uncertainty are sufficient to describe the failure of the model. And we compare basically just the sum of them all with the weighted sum, and we see that what we get only with the entropy and aleatoric uncertainty, a boost of 2 to 11% only by the optimization itself. And that is actually 36 to 60% over using each uncertainty separately. And so a quick qualitative example, how would that look like in the real world? This image, these are the boxes that are removed. If we evaluate this on our IOU of 0.75, which is correct and which is wrong. Another example, you see, for example, it's the mostly truncated pedestrian or like shadowy areas. And then depending on how much you want your label quality to be, so if it's like, in this case, 50 or 75, you see that the bounding boxes that are removed differ in that case. And this one, that is here at falsely removed, but here correctly removed is only because it's in between these two thresholds and we optimize across the whole range. So what else can we do with that? If we don't find any mistakes in the model, we can also consider that as an auto-labeled or pseudo-labeled image, where you can see that even this pedestrian that is occluded behind the wall here is still perfectly detected, and the model is not making any mistakes in this image, so we can automatically assign it as auto-labeled, where here we have another example. So in short, what do we have? We define cost sensitivity for the detector, automate the thresholding process, investigate and optimize the combination of the different uncertainties and their role in failure recognition. We introduce different metrics and requirements for transparent evaluation. And what we end up with is a model agnostic approach. So it doesn't matter what detector you use. It's also application agnostic, as I said, that you could mainly define the budget depending on what requirements you have on your vision system. We have an efficient uncertainty estimation since we only use loss attenuation. The actual result of that is only an increase of 0.07% in the parameters due to the extension of the localization head. And in the end, what you get is a considerable reduction of the false detections and an improved performance of the detector. And in the end, mainly a free safety check for your detector at no relevant cost. And so if you're interested in the paper, there's the barcode. Please don't hesitate. Thank you very much.
Thank you so much for the great talk. So, questions from the audience?
Thank you for the talk. Would it be possible to pack everything in a single objective and just optimize it? Like you say, cost sensitivity, let's say the cost is the budget cost and the sensitivity kind of F1 score or something like this, and then minimize in one shot. Would this be possible or better performing in what you do?
That's a good question. Actually, what you could do is you could say that you don't want to define the budget. And then if you look at the ROC curve, you would say, I just want to optimize both the FPR and TPR, and you would get the best point, in this case, this point, that would give you the best out of both. But in general, why we went into a user-defined budget is that mainly this point, despite it being the optimal on both directions, it might be not the optimal for your use case, where you would say that, all right, I'm getting the least FPR for the most TPR, but maybe that's still not enough for the TPR that you would actually want. And therefore, we actually stuck to the user defined. And then if, I think that answers only part of your question, if I understood correctly. The other part would be if we have, instead of, let's say, this whole pipeline, whoop, just one whole system, which was a great question. I actually, someone asked it yesterday in the posting session. I would not know if you would get some conversions that would get you to good results. So I did not test if, for example, you could train a model on the whole thing directly from binary classification, correct, false, and the input would be the uncertainty. It could work. I would imagine it would mostly overfit and you would have to retrain it and you have less transparency in that case. But that would be a very interesting future direction.
Thank you. Any more you have? Okay, in that case, I thank you again for the great talk and I invite the other one. So the second talk would be learning accurate and interpretable decision trees. Thank you so much for being here and presenting this. We have Mr. Sharma presenting this nice work.
Thank you for the introduction. Good morning, everyone. I'm Ravi. This is joint work with my advisor, Nina Balcan, on learning accurate and interpretable decision trees. Get started. Right. So modern concern in this era of neural networks is that we don't really understand what our machine learning models are doing. So they are extremely effective, extremely useful, much powerful than our classical models. But then the major issue is, can we even trust what they're producing, right? So there's no way of resolving critical things like whether there are inherent biases in this process of generating outputs. And the only way we can hope to resolve this is to actually understand what are the key factors in that are underlying this decision-making process of a model. And if it's an application like maybe a benign application like a virtual assistant, maybe you don't care too much because the worst thing that could happen, it makes a funny response. But if something critical like a medical application, like a diagnosis or a test you're performing or a treatment you're recommending, or in a criminal justice system, you're trying to make a decision about someone's life, you do want to be able to explain what predictions you're making. So in contrast to deep models, we have decision trees, which are naturally interpretable. So what's a decision tree? So each internal node represents some kind of a rule, which is a Boolean function of based off some feature. So it could be a real valued or a categorical feature, but then there's a Boolean function, and it depends on the output, whether it's true or false. You get a left or right node in the tree. For each example, you can go all the way down the tree until you reach the leaf nodes, which would give the prediction or the label class for that node, for that example. So that's a decision tree, and they are naturally interpretable. They are kind of a gold standard for what is an interpretable machine learning model. They have nice properties like access parallel decision boundaries, which is in contrast to a bunch of other machine learning models. Even people trying to introduce interpretability in other contexts like clustering, you would want to have things like access parallel decision boundaries, which are a natural feature in something like decision trees. But the challenge is it's hard to learn optimal decision trees. So let me give you some more context about some recent work, which is inspired by this, push for interpretability. So one challenge is decision trees are hard to learn, and some recent work shows that it's even harder than we previously thought. So not only it's hard to get an optimal decision tree, for example, it's hard even to approximately optimize a decision tree. So there are more and more, hardness results being shown about getting perfect decision trees or even close to perfect decision trees. Another recent line of work is faster optimal decision trees. So these are exponential time algorithms, but they are like, faster exponential time algorithms. So there's another push for trying to just speed up whatever you can do. So these approaches would work nicely on relatively small size trees. Uh, so in contrast to these two directions, we propose a new learning perspective for decision trees. So it's a fresh perspective for how to approach decision tree learning. So we use this paradigm called data-driven algorithm design. Essentially, you consider a family of algorithms and you try to characterize that family by some real valued hyperparameters. And the goal is to learn these hyperparameters from a collection of multiple data sets. Instead of a single data set, X and Y, which are the features and the labels, you assume you have a collection of multiple data sets. They could represent different related tasks. Or it could even be like, chunks of the same task, but maybe from different sources. But we assume that there is some connection between all these data sets, which we model by some fixed but unknown distribution, which is used to generate these individual data sets. So this is kind of like a meta distribution over your data sets. So under this framework, what we want to do is want to give a bounded number of samples that are needed to effectively learn near optimal hyperparameters. So we want to give a guarantee that our learned hyperparameter performs nearly as well as the best possible parameter for the distribution and expectation. Under this framework, there's a quick summary of all the contributions that we do. So we look at various different aspects or techniques that have been used for learning decision trees. Some of them naturally at hyperparameters, some of them we design and propose new hyperparameter families. And our contribution in each case is to give the bound of the sample complexity. And in some cases, we're able to even give efficient algorithms for learning these hyperparameters. So the first contribution is to top-down decision tree learning, where the key ingredient to the algorithm is the splitting criterion. So that says when you're building the tree top down, you want to figure out which node to split next and which rule to use when you're splitting that node. And in this case, we give a novel algorithmic family which unifies existing heuristics like entropy, Gini impurity, the current Mansour criterion, which is a theoretically principled criterion, which is like theoretical guarantees. So the idea is no single heuristics works well across all data sets and domains, but if we unify them, we have a single family and we try to learn over that family what the best heuristic is, we can potentially do well across all data sets. And so our contribution here is to give a sample complexity guarantee on the selecting the best splitting criterion. We also give bounds on hyperparameter selection Bayesian methods. So it's a randomized algorithm which starts with an initial tree skeleton based on some prior, and then does a stochastic search. So I'll go into the details in a bit, but the idea again is we are able to apply our techniques even to randomized algorithms which have some hyperparameters. Another useful thing in decision trees is to prune a decision tree. So once you've learned a tree, it might be too large, it might overfit your training sets you care about pruning it, and there are several techniques to do this. And again, in some of those techniques, there are hyperparameters which you should have in tune. And finally, so most of the techniques in the literature have cared about just the accuracy of the final decision tree, and we do want to explicitly encode interpretability, and in the context of decision tree, one naturally to define as the number of leaves or the size of the decision tree. So we add that as a cost to the objective itself. So we want not only our learned model to work, generalize well, have low error on the test samples, but also result in smaller interpretable trees on new instances. All right, so let me start with the splitting criterion. So I'll quickly summarize what the top-down decision tree process is. It's a simple algorithm. So you have an input and node function class. So this is a set of splitting rules you could use at any node inside the decision tree. We assume it's a finite class. We assume we're given the size of the tree, and we are given a fixed function, which is a splitting criterion. We start with the leaf node, and while we have at most t nodes at each round, we would split the leaf node, which using the function which maximizes. So we have to select two things. We have to select the leaf node and also the splitting function to apply to that leaf node. So for all combinations of leaf nodes and node functions, we want to find out which one maximizes the splitting criterion. So the splitting criterion takes into account the data set, how it gets split by applying the node function f at any particular leaf node L. Yeah, so maybe we start with a single node. We figure out that this particular splitting criteria splits this initial single node in the best way. And maybe out of the left and right nodes, it's maybe the right node. When we use the criteria h greater than 50, that gives us that optimizes the splitting criterion, and then we split that and so on. So the key decision when we're trying to build the tree in this greedy fashion is to decide which node to split and how. So in the past, people have used a bunch of heuristics. So even if you go in, and try to implement using existing implementations in Python, you will see like a bunch of different criterions listed. And as a practitioner, your goal will be to, maybe do some kind of trying out each one of them and see which works best for your data set. But our motivation is to try to get a much more powerful class, which includes the existing criterion, but also kind of automate this process of selecting the best hyperparameter. Right, so there's empirical research, which has been known for decades at this point, which suggests that different criteria work best on different data, and the best thing we know is just go in and check out each one of them. And we propose a new criterion, a hyperparameterized family, which is a single criterion which interpolates all these, and it's an infinite family, so includes a lot more other ways to split the decision tree. It has two hyperparameters, alpha and beta, and so it can be used to recover all the existing known criteria for specific values of alpha and beta in our family. We can recover the existing criteria. So the figure on the right shows performance or the accuracy on different data sets as you vary these hyperparameters, so that you learn a different decision tree because the choice of the hyperparameter impacts the entire learning process. There can be remarkable differences. So the brighter shades indicate higher accuracy. So not only within a single data set, there's a large amount of variation as you vary the hyperparameters across data sets. Different hyperparameters lead to optimal results. So you do really want to learn that hyperparameter, which is specific to the individual data set. And motivated by that, we present a theoretical result. We show that we can learn to tune the best hyperparameter, alpha and beta, using a polynomial number of samples, which depends on the size of the tree that we're trying to learn, and also the size of the node class which we're working with. So just to give a quick insight into how we approach this, our analytical approach is to analyze the accuracy of this of the learned tree as a function of the hyperparameter on a fixed problem instance x1. So we fix a problem instance, vary the hyperparameters, and see how the learned decision tree varies. We do an induction on the top-down rounds and give a bound on the number of distinct behaviors this algorithm can potentially achieve as you vary the hyperparameters. And this bound on the number of distinct behaviors implies a bound on something called the pseudo-dimension, which is a generalization of the well-known VC dimension to real-valued functions, and gives a bound. It gives a bound on the. There's using classical results from learning theory, it gives a bound on the number of crop samples that you need to run. So moving on to the second application, we also have Bayesian methods, which are also an alternative way, but also pretty successful in learning good decision trees. So it's a randomized algorithm which starts again with a single root node, but then you split these nodes randomly. So you have some probability of splitting, which again involves two hyperparameters. So this is the already proposed approach, but it has hyperparameters which we are not sure how to set initially. And then once you've split the nodes, you apply a random splitting rule at each of these nodes. And this results in a skeleton. So we start with that skeleton and consider a small modification. For example, we add a node, delete a node, or swap out one of these splitting rules. So this results in the next candidate tree, and we move on to the next candidate tree. In the sort of Markov chain, we decide we use a Dirichlet posterior to decide the probability with which we want to transition from the current tree to the alternate tree. And after a certain number of iterations, we hope to converge to a nice tree. But here, sigma and phi are tunable parameters, and our work shows how to tune these parameters and number of data samples you need to tune these hyperparameters. Right, so the goal is to tune them in order to maximize the expected accuracy of the learned decision tree, which, for data sets which are sampled from some fixed but unknown distribution. Our insight is we analyze the structure of the loss as a function of hyperparameters, but since it's a randomized algorithm, we analyze it for fixed random bits. So we assume that, the learner has already flipped some coins and figured out all the randomization they're going to use. And for those fixed random coins, you can analyze the structure of the loss as a function of the hyperparameters, which it turns out is a piecewise constant function in this two-parameter space with exponential boundaries, and we give about the number of distinct pieces we can get in this loss function. With that insight, we are able to show again a bound on the number of samples needed to learn a near optimal hyperparameter value. The nice thing about this case is not only the sample complexity nicer, but just because we get a polynomial number of pieces, it also gives relatively more efficient way to actually learn the hyperparameters in this case. Right. Our next application is to pruning decision trees. So that's when you've already learned a decision tree, but you want to post-process it in order to maybe remove some of the nodes that you learned because either they're redundant, they're not adding, just making the things more complex and less interpretable, or sometimes even worse, they can just overfit your training set and actually reduce the generalization power of the decision tree that you learned. So for example, in the left branch in this tree is completely redundant and just makes things less interpretable. So you could just remove it and replace it by a single leaf node. So there are several methods to do pruning. We focus on what is known as the min cost complexity pruning. So, we know if we maximize just the accuracy and we don't care about anything else, it will lead to potentially very large trees and overfitting the training set. But on the other hand, if we add small additional cost to the size of the tree, so this is what this approach does. It has a tunable hyperparameter alpha, and then it also has a number of leaf nodes in the tree as a part of the cost metric. And as you vary this hyperparameter and try to optimize this modified cost, it would prefer potentially smaller and smaller trees, the more value you put on the second penalty. Right. So again, in this case, you're able to show that the best hyperparameter is data specific. You want to learn, in this case, the structure as a function of hyperparameter is actually pretty nice. It's a piecewise constant function. This implies we're using log T over epsilon squared data sets. We are able to learn from the data sets coming from a distribution what the best value of the hyperparameter is going to be. Again, in this case, we're able to give the algorithm for implementing this learning procedure is pretty efficient. So we have both data efficiency as well as computational efficiency. And to extend this line of thought further, just inspired by this, cost complexity pruning, we can add this number of leaf nodes as a penalty, not only in our training objective, and we can also add it to our test objective. In the sense, we want the final tree that we learn to also have not only good accuracy on the unseen data set, but also have small tree size. So we modify the test law. So it's very similar to the cost complexity pruning, but then there's a slight difference. But this allows us to control the accuracy and interpretability trade-offs, and we can essentially carry out the nice thing about our analytical techniques is they work with this new objective as well. So with this modified objective, which incorporates the tree size, we are still able to prove guarantees about how much data you need to learn the best hyperparameters for splitting and pruning or even Bayesian trees to simultaneously maximize this modified objective. So just to summarize, we have the following key takeaways. We show learning various decision tree hyperparameters is useful. So we, show in different contexts and different approaches for learning decision trees. So for example, the splitting criteria, in this case, we actually propose a new algorithmic family which unifies the existing heuristics, but in several other algorithms that are existing hyperparameters, which we show, which are analytical techniques are useful in giving provable guarantees about tuning these hyperparameters using multiple data instances. So we give formal bounds on the amount of data needed to learn good hyperparameters, and we are able to simultaneously improve both the accuracy and interpretability when we do this. Our work poses several interesting future directions. So in some cases, like pruning and the Bayesian trees, we are able to have some efficient algorithms, learning algorithms, but in the case of splitting criterion, the number of algorithmic behaviors is potentially exponential. So I think it's an interesting question to figure out how to actually do the optimization of the training. So our guarantees of the form that, if you optimize the hyperparameter on the training instances, you're able to give guarantees about any future test instance from the same distribution, but can we also do that optimization on the training set efficiently? And I think that's an interesting open question. We are also curious if our techniques extend to other interpretable techniques. We have upper bounds on our sample efficiency. So we are curious about tightness of our results. Can we give lower bounds? And finally, there are other interesting aspects like learning online when you're solving a sequence of problems instead of having a collection of problems. What if there are challenges of adversarial robustness? So there's several different aspects one could take here. Right. With that, I would like to thank you for your attention and getting.
Well, thank you so much. Now we have time for questions from the audience, please.
Hello. Can you give some interpretability to the alpha and beta parameters and what they represent and what are they trying to weight?
Could you repeat the question?
Can you give some interpretability over the alpha and beta hyperparameters? So what are they doing?
So yeah, I can go back to the slide. So the alpha beta parameters are so the alpha parameter actually already exists. The alpha Chalice entropy has been used in other contexts, especially I think as a regularization for online bandit learning. And by setting the alpha parameter correctly, you can get the best of both worlds, and you can optimize in stochastic as well as adversarial environment. So that's another application that people have previously seen. But the overall idea is we capture different ways in which, so the idea is when you're trying to split the tree, you want to make sure that split is sort of nice and uniform. And by controlling these parameters, you can control effectively how evenly split your data set is and how fast you're able to match with the labels that you're provided. So yes, the alpha beta, the beta parameter is a new one. It corresponds to the Kearns-Mansour criterion, which has some nice theoretical guarantees. So yeah, so I think the real idea is that it captures this different nice aspects of different existing heuristics by tuning them, by setting them to particular values. You can recover these existing heuristics and recover their individual nice properties.
All right, thank you.
Thank you for the nice talk. My question is regarding the fact that you presented your results in the improvement in accuracy or decrease in mixed classifications for hyperparameter to tuning or pruning. How do your results or bounds on sample sizes apply if the data set is unbalanced? So you have significantly more samples in one class than the other.
Yeah, so so the goal is to actually uniformly achieve improvement for a data set by learning what's best for that data set, right? So if you have the nice thing about our techniques is you can probably, so as we noticed that we not only the accuracy objective, you add a modified objective that you care about. In this case, we talked about the number of leaves, but also if you care about some other objective like you care about the accuracy on a particular subset of the data. Those are things you could incorporate and still be able to tune hyperparameters which meet those objectives. Yeah, but the interesting thing here is that you do need to tune them in a way which is best suited for a data set. And these are complex functions of the number of features and how they interact for a particular data set that decide how aggressively you want to split your decision trees and how you want to make those choices. But our approach is by optimizing over this large heuristic family, we don't need to worry about which exact heuristic works well for which combination of features. We can just do a learning over the training set for which features work well on a given data set, and that's enough. And we don't need to worry about additional properties of the data set.
Thank you. Do we have more questions from the audience? Online questions? All right, so thank you again. Okay. Welcome back to our FIPS oral session, learning algorithms. So we have with us our next speaker, Sabina. She's gonna present this work, Bayesian active learning in the presence of nuisance parameters. All right, thank you.
Cool, thanks. Hi, everyone. I'm Sabina Sloman. I'm a postdoc at the University of Manchester, and I'm going to be presenting some joint work with Ayush Bharti, Julien Martinelli, both of whom are here at UAI, and Sammy Kaski on Bayesian active learning in the presence of nuisance parameters. All right, so many of the problems many of us sort of face are kind of characterized by this property that collecting training data is costly. Collecting training data might mean running an entire experiment, collecting an expensive measurement, or retraining an entire model. And we have like a fixed budget, right? So it's only feasible to collect some kind of small number K inputs. And what active learning methods, like the one I'm going to talk about, do is they kind of provide you with a systematic way to select those K inputs to be as informative as possible. So this is just kind of a overall sketch of what a generic active learning method looks like. So start with some estimate of your favorite parameter theta, select your input X, observe the corresponding output, update your estimate of theta, kind of given these data, and then kind of use this updated estimate to inform your selection of the next value X, and then you kind of continue on this loop until your budget runs out. And the sort of key idea here is that you want to build this design step in such a way that it improves your inferences. And so what I'm going to kind of talk about today is show you some situations in which Bayesian active learning, which is sort of a version of this design loop, can actually hurt instead of help inference. If you've heard of methods like a sequential optimal experimental design, this is the same thing as an active learning. And as you may have guessed from the title of this talk, the sort of key ingredient that's going to kind of break things down here is the presence of nuisance parameters. And so kind of roughly, these are things that capture uncertainty about ostensibly uninteresting parts of your data generating process. All right, so I'm going to sort of try to lay some groundwork here without nuisance parameters, and then I'll bring them back in a couple of slides. But I'll denote our inputs X and our outputs Y. Your learner specifies a model or a likelihood function that assigns to your data a conditional probability. What is the probability of my outputs Y given my inputs X and theta? And I'll refer to theta as your target parameter. The goal of learning here is to kind of learn what is this value of theta. And because this is a Bayesian method, we'll assign to theta some prior probability distribution. So you can sort of assess the prior probability P of theta for any sort of allowed value of theta. And then doing inference here consists of an application of Bayes' rule, so you can compute the posterior probability of theta kind of given some data that you've observed. Okay, so our goal here is to learn as much about theta as possible. So we're going to set up this kind of design step of that active learning loop in a way that we gain as much information about theta as possible. So luckily, the literature gives us some kind of really nice measures to do this. So this is a measure of the expected information gain, or EIG, about theta. This equation here is kind of the heart of Bayesian active learning. Bayesian active learning basically selects the value of X that maximizes this equation on kind of each iteration of that loop. You can see the expected log posterior to prior odds of theta. Basically, how much does your kind of posterior believe in theta after seeing some data versus before? Hopefully this strikes you as kind of a somewhat reasonable measure of the amount of information you've gained about theta. Of course, you're the learner, you don't know the value of theta, so you take an expectation with respect to your prior. Now you have the expected information gain. I can rewrite the kind of numerator that's a posterior on probability using a Bayes formula. These p thetas are going to cancel out. And now I've sort of written on the EIG as a function of what is the likelihood of my data under theta versus what is sort of the marginal probability of my data. Hopefully it'll be clear later kind of why this is nice in our setting. Another way to sort of see that this is a reasonable measure of information gain is to notice that it's just the mutual information between this kind of random variable theta and the random variable that's usually there. All right, so this method of sort of selecting the value of X that kind of maximizes this equation on each iteration and then kind of doing inference based on that, this method provably works in the sense that, you know, given some assumptions, it'll give you the right value of theta with relatively high precision. All right, so now, like I promised, we'll sort of complicate things out with nuisance parameters. And basically all we're doing here is we're going to partition this parameter space. So now you have your target parameters theta, things you don't know about, things that you want to know about, same as we had before. And now you also have your nuisance parameters, which I'll call psi. So these are things that you don't know about, but you don't particularly care about knowing them. They're just sort of these sources of uncertainty that you're kind of including in order to have a fully specified model. So now you have your likelihood function. That's kind of a function of X and theta and psi, and you're kind of assigning a joint prior to both theta and psi. Okay, so what I'm showing up here are all sort of problem settings to which Bayesian active learning has been or has proposed to have been applied. And what all of these have in common is that kind of solving the problem doesn't actually require a full characterization of the data generating process. You want to just sort of hone in on some small part of the data generating process. So for example, take the problem of model selection. Here your goal is to identify the correct architecture or the correct sort of structure of your model. This is your target parameter. Maybe you think that the structure will kind of generalize to new participants or new task environments. You're also uncertain about the parameter values of this model, but you kind of don't care about that as much. You don't think that these specific parameter values will generalize to your next participant or your next environment, so you treat these as nuisance parameters. All right, so again, even in the presence of nuisance parameters, what we care about is, are we learning theta well? So our design step is actually going to look very similar. We want to select the value of X that sort of maximizes information about theta. I'm going to refer to this measure as the expected target on the information gain, just to kind of disambiguate it from other information theoretic measures I'll kind of talk about later. The key sort of difference here is that in practice, when you actually compute this, you want to kind of take into account the fact that you're implicitly marginalizing across these nuisance parameters. So in particular, notice here and here, you kind of have this likelihood, what is the probability of my data given theta? This is an implicit marginalization across your prior over nuisance parameters. And so now we can ask the question, kind of will sequentially maximizing this equation give you the data generating value of theta with high precision? Okay, so far, I've kind of given you a lot of framework and a lot of notation to sort of reason about the learner's beliefs about the data generating process. But in order to kind of get at this question, we're going to want to sort of say something about what the data generating process looks like. So in the extended formulation of this that we introduce in the paper, we sort of introduce a bit of a framework to kind of reason about this data generating process. And in particular, we're going to assume that your data is generated by some value theta star and some distribution over your nuisance parameters q psi. And so this induces a data distribution, q of y given x, which is your probability of y given x that depends on theta star. and integrates over the entire distribution of nuisance parameters. Importantly, this data distribution is implicitly conditioning on theta star. That's just sort of by construction, we've assumed there's kind of one stable value theta star that's generating on your data. So sort of asking the question like, what will the data that the world generates look like is the same as asking the question, what will the data that the world generates under theta star look like? So we'll assume that the learner can sort of evaluate this conditional probability P of y given x for a particular value of the target and nuisance parameters. But we're not going to assume that their prior over the nuisance parameters is well specified. And so what this means is there's a sort of true distribution of nuisance parameters Q of psi, and the learner's prior kind of even conditioned on this true value theta star may not necessarily be equal here. Okay, so now kind of given this, I'm just going to sort of return to this active learning loop and use sort of all of this that I've built up to kind of give you a more concrete sense of exactly what our setting looks like here. So we have our prior beliefs over our target and our nuisance parameters. Our design step consists of selecting the value of x that maximizes this expected target information gain. We observe a sample from the kind of data distribution that this induces, which again, this depends on theta star and Q of psi. And then we compute our posterior of theta as a function of our sort of assessment of the likelihood of our data given theta, which will depend on our prior over nuisance parameters. And maybe you're already sort of starting to see a bit of what the problem is here. There's a mismatch here, right? Between the way that we're computing our prior and the way that y is sort of actually generated. All right, so now we want to kind of say something about you kind of, in this setting, how much will the learner sort of actually be expected to learn about theta, to converge on this data generating value of theta. To do this, we want a measure of how much information the learner gains about other target parameters. Luckily, we kind of have this for free in our setting. It's our acquisition function, the expected target information gain. What's a bit kind of unsatisfying about this is that this equation sort of absorbs all of the learner's epistemic uncertainty. The learner doesn't know what the true value of theta is. The learner doesn't know what kind of data they'll see. So they take this expectation with respect to their prior. But now we've kind of done this work to build up this framework so we can sort of say something about the data generating process in a way that sort of dissociates from the learner's prior beliefs. So now we can ask not only how much information can the learner expect to gain, but kind of given a particular data generating process, how much information will they gain? So I've done two things to this equation here. First, I've replaced this sort of generic instance of theta with theta star. This indicates that what we care about is not just that the learner converges on some value of theta star, on some value of theta. We care, do they converge on the data generating value of theta star? And then also in this outer expectation, I've replaced the terms with ones that sort of characterize the true data generating process. And then up here, this kind of the learner's assessment of the probability of y given x, this still depends on the prior over nuisance parameters. And this is kind of because when the learner sort of ultimately does their inferences, when they compute their posterior probability of theta, it will be on the basis of their prior. They have no better source of information. And so that's kind of reflected in the fact that we're keeping this prior here. Okay, so now we have this measure, the target information gain, R star. And the way you can interpret this is sort of given a stream of data from a particular data generating process, how much can we expect the learner to be able to identify the value theta star that generated those data? So notice if this quantity is less than 0, that kind of indicates that the learner's posterior sort of believes less in this value theta star than their prior did. In other words, acquiring data is hurting. It's giving them a kind of biased inference of what theta star is. If this happens, we refer to it as negative interference. And so what the sort of theoretical results in the paper do is they basically take this quantity and then we ask questions about it, like when can it go below 0? How far below 0 can it go? So before I kind of get to those results, I'm just going to kind of summarize what they're going to say. So what we're going to show is that nuisance parameters can lead to negative interference. In other words, in the presence of nuisance parameters, the acquisition of data can bring the learner's beliefs away from theta star. And so the implication of this is that learning in the presence of nuisance parameters requires meeting two objectives. So one, you want the learner to prevent negative interference. You want to ensure that when the learner changes their mind, they're changing it in the right direction. And then given that, you want to gather data to efficiently update your beliefs. And so the problem that we're going to sort of identify here is that standard approaches to Bayesian active learning pursue the second objective to the potential detriment of the first objective. All right, so the first question we want to ask here is, does negative interference occur? And if so, when? As I've been sort of alluding to, the kind of key problem here is a mismatch between the learner's expectations of what data under theta star will look like and what the sort of data generating process conditioned on theta star actually looks like. And we can measure the size of this gap using the Kullback-Leibler divergence between these two distributions. And I'll refer to this as a measure of misspecification of the target likelihood. So this is the degree to which sort of the learner's assessment of the likelihood of data under theta star under their target parameters is misspecified. And we have a proposition in the paper that kind of shows that this target information gain depends negatively on this misspecification term. And so we can say that negative interference occurs when the target likelihood is sort of relatively misspecified. The target information gain can be negative when this term is large. So this is what happens when I remove the nuisance parameters. Now these two sides are equal, and the misspecification is gone. We can cross out this term, and now we've written our target information gain as a divergence measure, which can't be negative. And so the implication of this is that negative interference can occur, and it can occur due to the presence of nuisance parameters. In this setting, when we remove the nuisance parameters, this kind of danger of negative interference goes away. Okay, so we kind of have, we know this is a problem, but how bad can it be? The short answer is it can be sort of arbitrarily bad. So you could collect some observation. This could induce a bias on theta star so extreme that no matter what finite amount of subsequent data you collect, you can't kind of unlearn the bias you've induced. The longer answer is a theorem in the paper. Okay, so, you know, we have this problem of biased inference. We know it can be really bad. We might want to do something about it. What can we do? You probably saw the answer here coming, but you would want to learn the distribution of nuisance parameters. And again, we kind of show this in a bit more of a concrete way in the paper. But what I sort of want to talk about for the last couple of minutes is kind of, given these results, what can the learner do with these results? So we can think about the gaining information about the value of these target parameters as like the learner's primary objective. And what all of this is sort of really building up to is that in order to achieve this primary objective, the learner has sort of this other implicit auxiliary objective. They need to gain information about the target likelihood, and they can do this by gaining information about the distribution of nuisance parameters. So to sort of represent this objective, we define a analogous information theoretic acquisition function, the expected likelihood information gain. So here you have the mutual information between this distribution of nuisance parameters conditioned on theta star and the data distribution. Of course, in practice, the learner doesn't know the value of theta star, so they can take an expectation with respect to their prior. It turns out you can kind of decompose this equation into two terms. And the term on the right is equivalent to the negative of this acquisition function encoding their primary objective. And so what this implies is that by selecting the value of x that kind of gives you really high values on this expected target information gain, you might actually be reducing the amount that you could gain on your auxiliary objective. And you could be reducing the amount that you're doing to reduce this threat of negative interference. And so in a couple synthetic experimental settings, we kind of show that, in fact, the values of these acquisition functions do tend to be negatively correlated. And yeah, and then to conclude, kind of what we've shown is that a standard approach to Bayesian active learning pursues only information about the target parameters. But this is only one of two objectives the learner needs to meet in order to learn effectively in the presence of nuisance parameters. And that pursuing information about the target parameters can be to the detriment of pursuing information about the nuisance parameters. And so when I said at the beginning that sort of these methods can hurt rather than help inference, this is what I mean, is that they can sort of fail to take steps to prevent negative interference. Thanks for your attention. Any questions?
Thank you so much. So, questions from the audience, please.
Thank you for your talk. I'm wondering because here it seems that misspecification is between your prior distribution P psi given zeta star and the true distribution Q psi. So is it possible that even if the data generating process is also misspecified, so the P y given x zeta psi, this is also misspecified in the model would happen if it would be even more detrimental to the using expected information gain as the acquisition objective?
Yeah, that's a great question. So yeah, you're right in kind of pointing out that we're sort of looking at this kind of, so you can distinguish between kind of prior unmisspecification, is your prior over other parameters unmisspecified, and model unmisspecification, is the sort of likelihood function unmisspecified. And we're kind of looking at the sort of intermediate case where it's because your prior is misspecified, you kind of have a biased estimate of this likelihood, but if you did get it's sort of, you can remedy it by kind of learning on this distribution of nuisance parameters. I think you're right that the results here absolutely apply to this case of model unmisspecification. There's a little bit of work on kind of how model misspecification interacts with these methods that I'd be happy to kind of chat with you after about. But yeah, short answer is I definitely think it applies kind of very, very closely.
Thank you.
More questions here? All right, so in that case, let's thanks again our speaker.